Hello. In this video, I'd like to share certain information with you. We will cover the concept of building, and then we are going to move to architectural design process, environmental system, building products, the concept of structure, and basic components of the structure. So let's start with the first one. Why do we need buildings? What is a building? First of all, we all know that that's an English word, but in Turkish, there are two different words as if you want to translate it. The first one is yapı, and the other one is bina. We use both of them in Turkish, but yapı is it has this Turkish origin, but bina comes from Arabic language. Uh, and they have different meanings. But we don't have the same for the English. We only have one word, building. And throughout the semester in these videos and in the classroom, I'm going to share Turkish terms with you. It doesn't matter if you're a Turkish student or not. Uh, it'll be very good for you, very useful for you to learn the Turkish words as well. So let's take a look. What's the difference between yapı and bina other than their origins? Uh, can we live in an environment like that? Can you imagine yourself right at the moment you are staying on this couch and you are in this wilderness? There is nothing around you, and you are trying to listen, watch the video that I'm providing for you. Is natural environment, is this environment suitable for us to live a healthy and comfortable life? Will we be uh, comfortable there? Will we be healthy uh, on this couch? Uh, this is what we need. We need a basic shelter. We need to be protected from certain things. As you can see, this is maybe the most primitive building that we can say. Uh, we need to be protected from the harmful rays of the sun or excessive heat. We need to be protected from the wind or storm or rain or some wild animals, we can say. There can be some other examples here. So the building can be defined as a new man-made environment. So it's an environment, but it's made by man, created by humans. It's not natural, but it's not artificial either. Uh, it's a man-made created environment which is formed by selecting, enclosing, and reorganizing a part of natural environment in order to provide a suitable living area. So we have this natural environment at the beginning, the whole area, untouched area. This is what we do. We select a part of it and we create a sort of envelope, a boundary, and we reorganize the inside part so that we will have a, a living area for the user. Uh, that's what we do it. We reorganize this inside area so that our user can have a comfortable and healthy, suitable living area. And it's not necessarily have to be over the earth. It can be over the water or inside the water or inside the earth, like the school. This is a, a floating school designed by NLE architects in Nigeria. Uh, and this is a school building. Yapı versus bina. Yapı is we can define it all man-made constructions which can be on or inside the earth or water for habitation or for prosperity. Anything that has been created by man, such as dams or bridges or roads, these are all constructed things or tunnels, but including the buildings. But when we say bina, building, we uh, we want to talk about a specific group, subgroup of this yapı, if we say. Bina is the buildings or constructed things that we spend our life in it for a short or a long period, like this school building or a hospital building. Uh, so everything made by man can be defined as yapı, including bridges, dams, or tunnels, or buildings. But bina is more specific for habitation, uh, residential buildings, school buildings, hospital buildings. This is the subgroup of yapı, if you will. So we covered the building. Uh, let's have another question. How do we obtain buildings? Here we see a process which we call architectural design process. This is the way or a method or the time period that we do in order to obtain buildings. Uh, Design. Simply, we can define the activity of designing as making a series of decisions, step by step decisions, and at the end, we will have a functional işlevsel, which is işlevsel in Turkish, and aesthetical properties. At the end of these steps, these decision steps, we will have something, we will obtain something. Uh, it can be a building, it can be a car, we can design a book or something else. And that object, that designed object, will have both functional and aesthetical features. And uh, what we mean by functional and aesthetical features. Let's examine it over this simple example. This is a washing machine that we are all familiar with. When we say functional properties, uh, we need to talk about the function of this machine. It functions to wash the clothes, or it functions in order to clean the clothes. We want to get the dirt out, away. So someone, probably an engineer, make a series of decisions, and at the end, there are some features or properties of this machine which works in order to execute the function, such as this middle part. It has this diameter. Someone decided that it needs to be this centimeters. Or this machine part, an engineer decided that it will consume that amount of electricity. And if there is a problem with these decisions, if there is a problem with the calculations, then it will not function as intended. It won't clean the clothes. These are the functional properties. Uh, and there can be some other aspects, such as the color. It can be a black machine, it can have this orange color or red color, or we can change the shape. It doesn't have to be this prismatic shape. In this prismatic shape, we can change the position of the lid or the shape of the lid. And we can easily say that these are some aspects that do not work for the function, but works for aesthetical beauty, if we want to name it. That's how we perceive beauty. Uh, we cannot say that this orange machine functions better than the white one. Or we cannot say that this machine, this shape, this geometrical form, will get the clothes more cleaner or cleaner. It's impossible to say that. But there are certain aspects, of course, we won't be able to separate as functional or aesthetical features. These may work for both of them. Uh, so uh, let's have another example, this time more architectural example. This is a wash basin that we are very familiar with. It works in order to wash our hands, wash our face, and brush our teeth. And this is the most common shape. It has this part. generally wide. It can has this support part, or it can be wall hang, uh, or more rectangular without these curves. Or if the properties of the user changes, the these aspects will change accordingly. If the user has to use a wheelchair, then this height will change, and there will be some additional parts so that they can hold on to that. And these decisions, someone decided that this rectangle has these sizes. It will have this color, white color. If the user has to use the wheelchair, then it will has this additional curve and these parts, support parts. And if there is a wrong decision about its height, about its size, or if someone forgets to put these support parts, then it won't function as intended. Users will not be able to wash their hands in a comfortable and good way. But what happens if we just concentrate on the functional aspects and just ignore the aesthetical values? Then we can end up in a situation like this. As you can see here, it's something that I see on the internet. It's the texture. Uh, these are not dirts. It's not dirty. It's the texture. They make these decisions so that it functions. There is no functioning issues or problems with this wash basin, but they ignored the aesthetical part, and at the end, it looks unpleasant. Uh, or we can try to aim for both of them. We don't need to prioritize one of them over the other one. We can have both functional and aesthetical designs, such as this one. It doesn't necessarily have to be white in white color or in that ordinary shape, standard shape. We can change the shape. We can change the visual aspects, appearance. We can create different forms, and they will both function. How can we make appropriate decisions so that we will have functional and aesthetical buildings? During the architectural design, we make lots of decisions, a series of decisions, but it's very hard because they all affect each other. So, is there a way or an approach that can help us to make both functional and aesthetical buildings? Here, we need to examine the environment as a system. This is what we talked about. We take a part of natural environment, we create this boundary, we select a certain part, we create this uh, envelope, and inside the envelope, we create or reorganize a nice, comfortable, and healthy living area for our user. So this is the borders of the built environment or the building, we can say, man-made environment. These are the borders, the envelope, uh, yapma çevrenin sınırları, we can say. Binanın sınırları ya da mekanın sınırları. And these are all surrounded with this outdoor area, outdoor environment. These borders automatically create two environments. One of them is the outdoor environment, dış çevre, and the other one is the indoor environment, iç çevre, where our user uh, lives. So we can diagrammatize this system. If this is the boundaries of the built environment, then this will be the outer environment and indoor environment where we have users, one or more people. These can be young people, babies, or elderly people. Or users can be animals as well. And they are going to live in this indoor area where we have light, a sound, some air or temperature. And we are all, this whole system is surrounded with the outdoor environment, and there can be other human beings, other living creatures, plants or animals, wild animals, domestic animals. There will be non-living things, physical things like the sun, the wind, or other man-made environments like the villages or other buildings or airplanes or vehicles. And these all affect each other. Things in the outer environment constantly affect the building, the envelope, and the indoor environment, or vice versa. Something in the indoor environment may affect the boundary or the outdoor environment. And these effects, these integrated effects, can be in the both positive way or negative way, such as uh, our user will need to be in a heat level. If it's too hot, it will be uncomfortable or it can cause some health issues. If it's too cold, again, uh, uh, it can cause sickness for the user. So we need to keep the indoor temperature in between certain limits. But it's constantly being affected by the outdoor environment because there is wind, there is sun rays. If this part of the building envelope gets lots of sun rays, it will heat up and it will affect the indoor air temperature. Or if it gets lots of cold winds, again, the effects will be seen in the indoor environment. Another example, our user needs to be in a sound environment in the indoor area, and it needs to be appropriate for their activities. Like if they are sleeping, they need a quieter space, or if they are maybe making music or watching TV, it can have a louder tolerance. But again, it's all affected with by the outdoor environment. There are vehicles, there is traffic, air traffic, road traffic. There can be people, other people, cars, uh, or other buildings. Like there can be a carpentry uh, work area nearby or a factory, and these can cause all noises. And when the sound waves hit the envelope according to the properties of this building or this surface, uh, those noise waves can be reflected to the indoor area, and this can cause problems for our user. And these are the negative examples, but the effects can be in the positive way too. Let's imagine there are two users. One of them is sick and the other is not sick. They're healthy, and the sick one coughs. There are lots of viruses building up in the indoor air, and we need a nice air movement. We need to replace this polluted air with unpolluted, clean air. And in order to do that, we need to let the wind pass through this boundary to the indoor air environment and sweep away the pollutants. So this is what we do. We make decisions during the architectural design process, and at the end, we come up with this built environment, building and spaces for our users. And uh, that building's performance, its ability to meet all user requirements, all user needs, it's directly related to how these environments affect each other and how we are considering this effect during our architectural design process. This interaction occurs as the result of all decisions made during the design. If we decided to put a window or a door here, then it can let the air in, so all the polluted air can be get rid of. But if we didn't make that decision, or if we make a mistake uh, there, then all these build-up viruses may cause the healthy person, the other user, to get sick as well. And that's all because of our decisions. At the end of our decisions, what kind of a space will be created inside this boundary? What kind of interactions will this boundary create during its service life? How the outer environment will affect the indoor area, how the indoor area will affect the outer environment. Because we should always keep in mind that the main purpose of the boundary and the spaces, the main purpose of creating a building, a built environment for the user, is to provide a healthy and comfortable living area for our user. And we need to find proper solutions so that it will function as required. It needs to protect the user from all the negative features, the sun rays, the wind, wild animals, insects, burglars, etc., or noise. So we covered the environmental system, but how do we materialize our decisions? Because the architectural design process, it's all in our head or on a paper. Uh, it's all making decisions, but we need to uh, materialize all our thoughts, ideas, as solid objects in the physical world. How do we do that? And since it's so complicated, there needs to be so much decisions that we need to do, is there a system so that it will be easier for us to make proper decisions? Just imagine yourself. You want to make a pizza, and you get these ingredients, different ingredients, and you start chopping the tomatoes and mixing the flour with water, creating this dough, and you wrote them all together. But at that moment, you realize that you don't have an oven. So what are you going to do? If you want to do a nice pizza, then you need to make all these steps hierarchically. You need to follow certain order. Otherwise, if you didn't check if you have a working oven or not, uh, otherwise this will all go ruined. Because what are you going to do now? You just leave the uncooked pizza like that and go to a store to buy an oven and come back maybe in the oven will be delivered in 2 or 3 days a week, and during that time, that uncooked pizza will not stay fresh. It will go ruined. Uh, so it will be better to make the decisions or follow the or execute the steps according to a system. So how can we do that? Uh, we need to examine the building products. Uh, because the building is a very complicated, complex system, there are lots of different parts, and some of them are big, some of them are hidden under certain things. Uh, we need to have a classifying system so it will be easier for us to comprehend all this complexity. So we can examine the whole building in 5 different steps. These will help us a lot. If we learn it by heart, then it will help us a lot during our architectural design process. As you can see here, we have 5 levels: materials, pieces, components, elements, and units. Uh, Units are the biggest one. Here, a room, a bedroom, a kitchen, or a corridor. These can be all different units of a building, and a building may include lots of different units. And when you gather all these different units together, you will have the building. But how can we create a unit? In order to come up with a unit, have a unit, we will need elements. As you can see, walls, floors, these are different elements. And when we gather them up, when we collect 4 walls and 2 floors, then we will have a unit. And in the other level, we are going to see the components. In order to create an element, we need components, different components, like this brick, wall structure, window, or wall covering. When we gather all these different components together, we will have elements. And in order to have a component, we either need pieces or materials. We can have cement and we can mix it with water and we can use this mixture to cover the surface of this middle part so that we will convert that material into a component. Or we can take a pile of earth and shape it into one single brick and we can obtain many more bricks, gather them up, glue them together so that these pieces will create a component. If we change the material or if we change the shape, we will have a different piece. We can have a tree trunk and cut it into this shape and get four of these uh, sticks, let's say, and have this frame, and that will be a component. We can use either pieces to create components, or we can just directly shape the material into one single component. And when we gather all the components, we will have elements. The elements will create units, and units will create the building. So let's take a closer look to each one of them. Let's start with the units. So this is a building. It's a diagram and different parts of this whole structure, whole building is colored. And when we dissect it, and when we look at this picture, we can easily understand this part is going to be used as a unit. It's going to be the restrooms. And that part probably will be used as a theater. There will be another unit in a different shape, in a different location, again, to be used as the restrooms. Uh, and these are all different units. And all these units, when we gather them up, we will have the building. So we can define it like that. These units can be totally closed volumes. They can be semi-closed, as you can see here. The upper part is closed, three sides are closed, and the lower part is closed with the floor, but the one side is open to this courtyard, and that unit is called A1 in Turkish, A1 in English, or this can be totally open area like this terrace. So a unit or in Turkish we can call them yapı birimleri, birim. They are open, semi-open, or closed parts of the building which execute a function. They execute a function. This is a living room. This is where people sit down and talk to each other and have meals and uh, see their friends like that. And this is same. Uh, the function is the same. A1 is a typical or a specific living area with one side open. This can be for sleeping, then we will call it a bedroom. This can be for preparing meals. The function will be for preparing meals, then we can call it a kitchen. And these are formed by elements. So all the parts of a building, including the units, they are created by different elements. Eleman, öge, yapı ögeleri, yapı elemanları. These are integral products formed by combining the materials, pieces, and components to physically meet one or some of the functions of the building. So when we gather four walls and two floors, we will have a unit. And these are all elements. A wall is a building element. Floor is another element. And they will function in order to protect the user, in order to provide that healthy, comfortable living unit for the user. As you can remember, the main purpose of the building, the built environment, is to provide a healthy living area for the user, to protect it from negative features. So all these different negative features, all these different versions of protection will be divided among different building elements. Like this roof or this horizontal surface will function to protect the indoor area, so the user from the rainwater, from the excessive heat, and from the wild animals. Uh, However, this vertical wall element will protect it from the wind, not from the rain, or partially from the rain, but especially from the wind. Uh, or it can protect the user from burglars specifically. So all these different elements, they will be assigned for certain missions, for certain functions. Each one have different functions, different types of protection. And when we gather them all up, we will have units, livable, comfortable, healthy units. There are a variety of building elements, such as foundations, temeller, or floors, döşemeler, döşeme, stairs, merdivenler, structural system, yapı strüktürü, roof, çatı, or walls, duvarlar. And they will all function for different purposes. So we covered the units. These are the living areas, and they are created with building elements. Each element will be assigned with certain functions, certain types of protection, uh, and they are created by materials, pieces, and components. So let's jump to the first one, the first level. What's a material? Malzeme, yapı malzemesi, building materials, yapı malzemeleri. These are the basic products which are formed at the end of natural or artificial processes, and they do not have a definable geometrical form. They don't have definite shapes. They are amorphous. Like this stone, natural stone. It can be marble, it can be a granite stone, or different types of natural stones. It looks like a prism, but it's not. Or clay, kil, toprak. When we have an amount of clay, it will just create a lump, an amorphous lump. It won't have a definite geometrical shape uh, unless we uh, d give the shape to it. So metals like iron or copper, the ore, the natural metal, it doesn't have a different geometrical shape. Or tree trunk, wood, ahşap. It looks like a cylinder, but it's not. It's amorphous. So this is the basic level, the first level. And if we get a material from nature without a definite shape, and if we transport it to a workshop area or a factory, and if we give a definite shape to it, if we process it, then we will have a building piece, yapı parçası. Pieces are the every one of all objects which are made by forming the building materials for a spatial function, and they create a unity when we bring them together. Such as let's take a piece of marble, stone, natural stone, and convert it into this block shape, a marble block. Marble, mermer, is the material, name of the material. Block is the shape of the piece. And if we change the shape, instead of creating a block, if we create a panel out of the same material, marble, then we will have a different piece. These are all different pieces. Marble block is a piece made out of marble material. Marble panel is another piece made out of the same material. The difference is the shape. Materials, they don't have a definite geometrical shape. But if we provide a shape, like a block or a panel, a definite, definable geometrical shape to a material, then it's no longer in the first level. It is in the second level now. It's the piece level. If you get some clay and compress it in a mold into this rectangular shape, rectangular prism, then it can be called a clay brick, tulla. Or if you change the shape, then we will have a different piece. This time we have clay roof tile, kiremit. If you get some iron and cast it into this W or I shape, the letter I, if you look at the section here, then you will see an I shape, or sometimes in some countries it's called W profile. It's a profile now. It has a shape and it's made out of iron or steel. So it's a piece. Or if you change the shape and cast it into this panel or sheet, which has this zigzag pattern, which we call corrugated steel sheet. Sheet is the whole piece, and this zigzag pattern is the name. The name corrugated means that zigzag pattern, and it's all made out of steel. Çelik trapez levha, trapez corrugated. Again, the name of this shape, this zigzag pattern in Turkish. Levha sheet, uh, it's a piece. Or we can take a tree trunk, an elm tree, karaj, and cut it into this piece. Then it's a timber, kereste. If you change the shape, or we can change the material as well. Instead of elm tree, we can have oak tree, meşe, and create a panel similar to this one, shape-wise. Then we will have another piece, meşe, levha. And if you get lots of pieces and put them over one another or next to each other, then we will have a building component, bileşen, yapı bileşeni. Components are the products that have a specific place and function in the building and made by combining the pieces or shaping the materials. Let's get lots of steel W profiles. Or instead of steel profiles, we can have lots of elm timber. And we can create this structure. You can see it here. We place them to form a grid system. And we can nail them together or bolt them, connect them to each other. And that part in the middle of this horizontal surface will be called a floor structure. Döşeme strüktürü, döşeme gövdesi. That's the middle part of the element, floor element, one of its components. So floor is an element and it has many components. The middle part is called floor structure, döşeme gövdesi, one of its components. Instead of these profiles, if we change the material and the shape, the pieces, this time let's have lots of marble panels or oak hardwood panels, not one, but many, and place them next to each other, one another, to cover the upper surface of this floor structure. Then we will have another component, which we call floor covering, döşeme kaplaması, floor covering, another component, a different component than the floor structure, that middle part. And when we gather all these different components, this middle part, floor structure, one of the components, Another component, this top part, floor covering. We can cover the upper part if we want. We can cover the lower part. That's the ceiling covering, another component. And in the middle, we can have isolation layers, another component. And when we gather all these four different components into a whole unity, then we will have the element. It's the floor, döşeme. So each building element can be created out of components or materials. We need to have lots of components, gather them up together, and we can have an element. And that element will function in a specific way. So a floor will function to create the living area, a horizontal surface where people, furniture, and users can stand on, and that surface will carry their loads, their weights, and that horizontal surface will divide different living areas. Let's do one more example. Let's take lots of clay bricks, pieces, and gather them up by putting each one of them over the other one in these horizontal rows, and that part will create a wall structure. Wall structure, duvar gövdesi, duvar strüktürü, the middle part of the wall element. And instead of using bricks, we can have 4 or 5 or 10 steel profiles and again create a grid pattern, this time not horizontal but vertical, and that will provide the same component in a different way. Again, this will work as the wall structure, the middle part of the wall element, but it's totally different from the clay brick middle part. It's something different. It will function in the same way. Let's get all panels and use them to cover the outer surface of this middle part, middle structural part in these horizontal lines. Then we will have a different component. That's the wall covering. We can use different uh, pieces in order to cover the indoor surface, inside surface. Again, we can have insulation layers. We can have a window or a door as a component, and all these different components. One component, window, another component, wall covering, another one, wall structure. When we gather them all up, we will have this element, wall, duvar. Let's do one more example. This time I prefer elm timber, get like 20 of them, and create this structure in a different shape. The first one was the floor structure. It was totally horizontal. The second one was a wall structure and it was totally vertical. This time I create these triangles out of these timbers and multiply them so that I will have a different geometrical shape. And that's one of the components of the roof. Roof is the element, and this is one of its components, roof structure. Çatı strüktürü, çatı gövdesi. If I get lots of these clay tiles, I can use them to cover the upper surface of the roof structure so that I will have another component, roof covering. And when I gather all these different components, roof covering, roof insulations, roof structure, three different components gathered into one unity element, roof. How can we manage all these different parts to stay where we want them to be? We put them and we want them to stay there. We don't want them to fall down. We don't want them to collapse down. We don't want them to lose their form. how can we avoid everything to collapse down? We need a system which we call structure. In Turkish, it's structure. It's a French word, structure, same structure, and it can be defined as the system which keeps the form intact. This is a table or a desk, you can say, and we use this horizontal surface. We lean on it. We put our notebooks and books and computers and phones. So we want it to carry the weights, and we want this surface to be at this level all the time. We don't want it to fall down. But how is that possible? We need a system to keep that horizontal form intact. We don't want it to fall down. We don't want it to break into pieces. So there is a system, and we can easily see that there is this framework, and if we remove it, this piece of horizontal wood will fall down. It won't be able to stand at that level anymore. It will break into pieces. We won't be able to put our notebooks and write something on them. And that's because of thanks to this system that we call the structure. So the structure is the system that keeps the form intact, the form of any object, either the uh, table, either a building, either a glass or a drinking glass or a car. These all have structural systems. If you don't have a system, if you don't have a structure, then everything will fall down and break into pieces. They won't be able to keep their form uh, in that geometrical shape anymore. You remember this school building, right? And when we remove all the other elements, the roof, the walls, and everything else, and that form, that triangular shape, will be provided by its structure. Without its structure, if we remove the structure, then everything will fall down, buried in the water. Like this unusual shape for the building. Again, when we remove all the coverings, all the insulations, all the window panels, all the pieces and other components and other elements, the rest will be the structure, which provides its shape. Same with our bodies. We have this definite human form. It's all thanks to our skeletal system. Without the skeletal system, if we remove the system, then we won't be able to survive in this form. We will just uh, pile on the ground as an amount of meat and veins and nerves, etc. And there is this other term which we call construction. Construction in Turkish, konstrüksiyon, again the French pronunciation, yapım, the Turkish version, or inşaat, the Arabic word. These are all synonyms. Construction, it's different from the structure. Structure is the object. It's one of the elements of the building. That's something that we can touch. That's something that we can remove. But construction is not an object. It's not a physical entity. It's a process. It's the process of creating the built environment in the physical world. So it needs time and certain activities to be done step by step. And that whole time period, that whole process is called the construction. We can have the structure, the building, as the physical entity in the real world at the end of the construction period. Structure of the objects, structure of the building, mainly functions in order to meet all the loads and transfer them safely to the ground. Loads, yükler. These are the forces, all the forces. You remember this term force from your physics lectures in the high school. These are all the forces. There can be different types of these forces that act on a system like the head of the man here. When we punch the head, it means that we are we are directing a certain amount of force over the face. And at the end, either it starts to move, the face affect the force affect its motion. If it's standing still, it starts to move. If it's moving, uh, the properties of the motion, like the direction or the speed, may change, or it can affect the form, the shape, the geometrical shape. When I punch the man, the face starts to move. It was standing still before. Because of the force that I'm applying over the face, it starts to move and it's deformed. It loses its form, its geometrical shape, its integrity. So when we talk about a building, there are specific types of loads. The first group can be called static or dead loads. In Turkish, we call them durağan, static, or ölü, dead, yükler. And they are mainly because of these different building pieces and components. And since there is this gravity, the pulling force towards the center of the earth, they create certain loads. And all these loads needs to be met and transferred by the structural system of the building safely. Every object that we attach over the building, the coverings, roof coverings, wall coverings, this window panel, the floor itself, they all cause static loads because of the gravity, because of their weights, they cause loads. And they are, as you can see here, they are always directed towards downwards. These are downwards loads. And they create a constant force. The level of the load doesn't change. Their weight doesn't change. They are always there. They are always there and they always cast a certain amount of weight. Their uh, appearance doesn't change. Their weight doesn't change. These are called the static loads. And the opposite of static loads are these are vertical loads, düşey. They affect vertically all the time. And the opposite of the static loads are called dynamic or live loads. In Turkish, the same. Dynamic, hareketli, non-static, canlı yükler. And there can be some specific types, like the people, or furniture, or birds. These will create again loads, but they are sometimes there and sometimes not. If I'm standing on the floor, then I create this load over the floor. But if I move, if I leave the building, there's no load there anymore. Instead of one person, if we go there like five people, then we will cast a larger load. So the density or the level of the load may change. The presence of the load may change. If the bird uh, flies away, then there is no load. Instead of one bird, if there are five birds, the level of the load will change. So these are changing. These may change opposite to the static loads, which are always there and which are casting at the same amount of load all the time. these may change, their presence may change, their levels may change. And as you can see, they can be vertical loads as well. They can affect the structure in a vertical direction. Or there can be some lateral loads, yatay, horizontal this time, acting not vertically but horizontally or laterally, yatay in this direction. And these can caused by winds. When the wind blows over the surface of this building, then it will create this lateral load. Same with the earthquake. When the earthquake occurs, then it forces the building to move laterally on this horizontal direction. Sometimes there is this definite system that we can separate easily. We can touch, we can show, like these frames. If we want our pots to stand in this shape, at this level, we need a structural system, these frames. And if we remove them, the pots will fall down and crash into pieces. But in some objects, we cannot have a different shape or different system. Like this pot or this drinking glass, there is no separate system. There is nothing that I can point or touch as its structure. The whole object, its physical entity, is its structure. It doesn't need another system, a separate system to keep its form. Its form, its physical entity provides its structure. So we can see the same thing in the building, in a building. If we take a look at this picture, we can easily say that the whole envelope, all these vertical surfaces, the walls, it's like this drinking glass. There is no separate system. These walls, they carry the loads themselves. So the whole building functions to carry the loads. And these are called masonry systems, yığma sistemler. There is no separate structural system. The whole building is has also its structure uh, overlapping its physical entity, uh, like this drinking glass. Or we can create a separate structural system if we want. Mm, That those are called skeletal systems. Skeletal systems, like our body, like our skeletal system, like our bones. And if we remove that system, the whole building will collapse down. And it's a separate system which we can touch, which we can point out, show to our friends. In Turkish, it's called iskelet system, like that. That's the structure of the building, and else will be attached to this structural system. And the loads, all the vertical or horizontal, or all the static or dynamic loads will be met and carried and transferred by this system. The masonry building, the walls are the structural system at the same time. Walls provide that load transfer. But in skeletal buildings, walls are functioning to separate the environments, the indoor and outdoor environments from each other. The walls, they don't carry the loads because there is another system, the skeletal system, to do all the carrying thing. Like in this picture, we can easily say that these green lines, let's say, it's the structural system of the building. And we can see that we have walls here different from that one, different from this masonry example. If I remove these walls, everything will collapse down. The floors, there won't be anything left to carry the loads of the floors, the loads of the people, loads of the roof, and everything else. But here, if I remove this wall, nothing will happen. The structure is there because in skeletal systems, walls will not function to carry the loads. But in masonry systems, walls will carry the loads, the whole loads of the building. We know this building. It's Hyder Aliyev Center by Zaha Hadid, and it has this definite curvature geometrical shape. And how all these white panels be there, stand there at that level in this order without collapsing down. It has a structure. And when we remove all these white panels, we see these lines, blue lines, made out of steel profiles. And it's the structure of the envelope of the building. And we see other lines, surfaces, this time in a different color, in different sizes. They are not steel, they are concrete or supported with steel. And there are different structures for different parts of the building. These gray lines made out of concrete and steel, it's the structure of the whole building. These blue lines made out of steel, it's the structure of the envelope, the roof and the walls. So we can create structure for not only the building itself, but for different elements, such as the staircase. Let's imagine that this is what we design. We want to build that staircase in this form. We have two options, just like the masonry structural system or skeletal structural system for a building, we can create the same thing for the element, for this staircase. Let's imagine we gather an amount of concrete, beton. This is a mixture of cement, water, and sand, and some stones, and we can cast it in a definite form, and we can support it with these steel reinforcement bars. Bars, donatı, made out of steel, çelik, and we can cast it into this reinforced concrete betonarme shape, and it will stand on its own. There is no separate structural system. The whole object, the whole physical entity has its own structure embodied inside its physical entity. There's no other system. It's like the masonry building or this drinking glass. Or we can create the opposite, like that one, like the skeletal system of a building. We can have these steel profiles, like 5 or 10 of them, and we can create this structure first, the structure of the stairs, which keeps its form, which is a separate object, a separate system. And when we cover the upper parts, the lower part, the sides, then we will have the same shape, the same stairs. Let's do one more example. Let's imagine that we want to create this wall. It's an element and it has this curvative surface. I can have two options. I can have these bricks and pile them on top of each other on horizontal lines into this curvative form shape. Then it means that I'm creating a wall with its structure embodied to its physical entity. There is no separate system. Or I can do the opposite. I can have these either timber or steel profiles and hold them in a system like that, nail them or glue them to each other and cover the surfaces, fill the inside voids. And at the end, I will have the same form from the outside. It will be exactly like the first wall, the first, that one that we created. But there is this separate structural system. This time, not the structure of the building, but the structure of the element, the wall. And if I remove it, everything will collapse down. It's the skeletal version. Last question. How can we manage that all loads are transferred safely to the ground? Because that's what structure is all about. It needs to meet all the loads, it needs to carry them and transfer them to the ground safely. We need certain components. If the building structure is an element, it will have certain components. And these components will work to transfer the loads safely down to the ground. First, we have these horizontal floor surfaces. And then we see horizontal lines, which we call beams. And then we have these vertical lines, which we call columns. The transfer is starting from the upper side when we step on a floor as the users. When we put our furniture over the floor, we create loads, vertical loads. And the surface is the first component. Floor body is the first component that meets all these loads, and they need to transfer their loads to the other components, beams. So floors are the first components, floor structure, floor body is the first component that that meets the loads, and they need to transfer them to these horizontal lines, which we call beams. And beams, each one of them, will transfer their loads down to columns on their ends vertically. As you can see here, this is a problem. If we cut the columns in order to enlarge the space, it's very bad for the building structure. There is this risk of collapsing down. And all these vertical lines or surfaces which carry the loads and transfer them to the ground needs to be in the same direction under each other. Otherwise, all these loads will not be met. There is just void, nothing to meet and transfer the loads downwards. This is a problem. It needs to be horizontally and vertically intact, compact. Same with this chair. There is the surface, floor body, and there are four columns on each corners. Imagine a very fat person, a very heavy person is sitting on the chair. It means that the weight of the person will create all these loads, and these horizontal surface will transfer the loads down to the columns. And if the sizes or the locations or the connections of these vertical columns are not appropriate, if there are problems with the decisions, then they will all spread or break in pieces, and they won't be able to support the loads of the person anymore. They will fall down altogether, and there is this risk of hurting uh, that person or wounding them. So we need a system, a better system. Here, as you can see, these horizontal lines that we call beams, they work as like the belts that hold our pants on our waistline. It connects the vertical columns, it binds them together, and it helps with the load transfer. It with columns, the vertical lines and the beams, the horizontal lines, we will have a stronger structural system that can carry loads, more loads. So building structure is an element and it's made out of components. The first one, the horizontal ones that connects the vertical ones, are called beams. In Turkish, we call them kiriş. And the horizontal ones, these are columns. We can call them kolon or dikme in Turkish. Columns, these are the vertical ones, and they have all these loads from the beams. Static, they can be static loads, the loads, the weights of the building materials or the other elements, or they can be dynamic loads, either vertical or horizontal. Columns or studs, kolon, dikme, column, stud, they are the same word. They have the same meaning. These are subjected to vertical loads constantly, either because of static loads or because of dynamic loads. But columns work to meet and carry and transfer mainly the vertical loads, vertical loads. So they are constantly subjected to vertical loads. And when there is a storm, when there is strong winds, or when there is an earthquake, then they are also subjected to lateral, horizontal loads. They need to carry all these loads. So let's rearrange them. Uh, I will just take this one here up so that we can have two groups. First, the vertical loads and the lateral loads or columns needs to be created. They need to be created against to carry all these vertical and horizontal loads, and the level of the loads, they are important. Uh, if we have, let's say that we use very heavy building materials, very heavy roof tiles, very heavy roof structure, very heavy insulation materials, and it means that we are loading these columns over and over again. We are increasing the level of the load. And according to the sizes of these columns, uh, they will be under compressive loads, which we call basınç, compressive basınç. It means that all these heavy building products will be transferred. All the loads of the heavy building products will be transferred to the beams first, and all the beams will transfer their loads to the columns towards this direction. And underneath there is this ground surface, and we end up in a load or stress which will affect towards the center and cause the molecules of the column to be compressed. Sıkışmak, basınç. That creates a compressive stress. Since it's applied towards the center of the column, since it causes the molecules to be compressed, it causes a stress. That's gerilim. If the stress level is exceeded the limit according to the dimensions of the columns and the shape of the columns, there can be some bad consequences. So our columns needs to meet and carry all the uh, some of the loads all together. If the level is exceeded, if there is so much stress, and based on the sizes and the shape of the column, there can be some bad consequences. If we have a short and thick column, this is a short and thick column. And if we apply compressive loads over it, there is a limit, a safety limit. If the if we keep applying more and more loads over this short and thick column, and if we exceed the limit, the compressive stress will cause the column to be deformed. This is a deformed column. It has no longer its shape. Its shape has been compromised. So it was broken. It won't function regularly anymore. And that's what we call a compressive compression deformation, basınç deformasyonu. What happens instead of a short and thick column if we have a long and thin column? Again, if we exceed the limit of the stress, compression stress, it will deform, but in a different way. This time it will have this type of deformation. That's what we call a buckling deformation. In Turkish, it's called burkulma. You can easily remember from this image, if if your ankles cannot support the load of your body, then it can end up in the same deformation, burkulma. So this is compression. Compression loads act towards the center. What happens if we change the direction? If we have different types of loads which acts not towards the center, but from the center to the ends, to the outside. This is called tension. This one was called compression, basınç. This is called tension. It's çekme in Turkish. It affects it affects outwards and cause the molecules to be separated from each other, not compressed towards one another, but to be departed from each other. Let's take a look. Here we can see in detail now. They are applying more and more force, tension force, and it starts to deform. And if the limit is exceeded, it breaks into pieces. It won't be able to function anymore. What if instead of vertical loads, we apply different lateral loads out of wind or earthquake to a column? If the loads are applied towards the center, but not in a totally horizontal line, the first group is applied in the upper part, the other group is applied in the lower part, but they are in the opposite directions. They are both acting towards the center. Then these are called shear loads. In Turkish, we call them kesme kuvveti. And it's the basic principle of the scissors. If you want to deform or break a piece of paper into two pieces, if we want to cut it, then we need shear loads. This is how the scissors work. These blades, they are not perfectly horizontal or vertical. They are not aligned. They create two different forces very close to each other. And since the paper cannot hold, meet, and carry this shear force, it is broken. It is cut into two pieces. So, same with the column. If we apply wind loads or earthquake loads laterally, and if the shear stress exceeds the limit, then we see this type of deformation in our columns. These diagonal cracks, breaks, which we call shear deformation, kesme deformasyonu, kesme gerilmesi. And these are the loads or bad consequences when we think about the columns. Let's take a look at the beams this time, or the other word for the beam is called girders. They look like columns, but there are differences. First of all, they are not vertical like columns, they are horizontal. And they are subjected to both, again, vertical and lateral loads, but mostly the vertical loads because they are placed right under the floor surfaces, floor body, and all the loads that a floor surface gets, they are transferred to the beams first. So this is the upper part where the floor is attached to the beam, and the loads of the floor are applied over this upper line. And there are two columns that support a beam in these ends. And because of these columns, there are two opposite direction loads, this time upwards. And if we keep applying these loads, there will be a certain deformation in the beam. It will start to bend. In Turkish, we call it sehim yapmak. It bends. It will be deformed like that, and this is called sehim yapmak. Eğilmek, sehim yapmak, sehim. Let's take a closer look. The upper part, the molecules will be compressed towards each other. The distance between each molecule will be shortened. That's where we see compression loads, compression stress. But in the lower side of the beam, there's something different. This time, the molecules are not compressed towards each other, they are separated. The distance is increased between each molecule. And that's where we get tension at the same time. When a beam is subjected the loads, vertical loads, the upper part will be subjected to compression stress, and the lower part will be subjected to tension stress at the same time. And because of these different stresses, it starts to deform into this bending shape, like that. And this is what we call a bending deformation. So that means that we need to design our structural system. We need to make proper decisions for its vertical components, columns, and for its horizontal components, beams. We need to come up with proper decisions about their sizes, about their materials, about their connection styles, so that this whole structure, all the vertical columns and the horizontal beams and their connections and the systems, the structural system needs to meet, carry, and transfer all the loads, static or dynamic, vertical or lateral, safely to the ground without collapsing down, without these type of deformations. We don't want it our columns to be deformed under compression. We don't want our columns to be deformed under shear stress. We don't want our beams to be compressed, deformed under bending stress. The other difference between a column and a beam, apart from its position, can be its shape. When you take a look at the section part, we see a definite rectangle. We can use this piece as a column or as a beam. But if we prefer it as a beam, we should always keep it like that. Short side parallel to the ground, long side perpendicular to the ground. Like that. Not like this. This is something that we don't want. We don't want our long side to be parallel to the surface of the ground, short side to be perpendicular to the surface of the ground. Because if we place it like that, like this, like long side up, then it will be able to carry more loads without bending deformation. But if we place the same beam like that, then it will start to bend down. And if this man jumps, that means that the level of stress is exceeded, then its carrying capacity, then it will crack and fall into pieces and won't function regularly anymore. Always prefer that one for the beams. So it's all finished for this course. Uh, Hope to see you next week for a new subject. Thank you for listening.